This car runs on explosions, but what if it didn't? Internal combustion engines are kind of terrible at their job. 36 to 45 efficient at best. That means 55% of your fuel is just heat and noise and sadness. Electric motors 94 to 96% efficient. While I think some of the older ICE cars are super cool, modern electric cars more efficient, powerful and reliable. I want one of those for me. Could I just go and buy one? But actually no, I can't. What if I could swap the old ICE engine for electric motor? Today I'm going to show you what I've spent the past 12 months of my life working on, starting from electric motor. The plan? Well, open inverter board, Tesla motor and dangerous amount of optimism. I'm building this using Damien Maguire design files. Shout out to Damien for being way smarter than me and sharing his work with idiots like me on the internet. While learning KiCad and questioning my life choices, I decided, hey, why not modify the PCB layout as well? Because why make things easy? Oh, and I threw in ESP32 module for funsies. I sent out the design to JLC PCB, waited an eternity, more like 2 weeks, and the board arrived. Now comes the terrifying part, the first power up. This is where I find out if I made very expensive paperweight. I'm just gonna hook this up to 12 volts and ground and let's power it on. LED is on. Yes, we have a light. The input is 12 volts, outputting 5 and 3.3 volts on the board. Measured everything, all in range. We didn't make fire. Well, that's a win. Okay, before I get too excited and solder the missing bits, let's see if the main brain actually works. Time to program STM32. Connecting the programmer, plugging into the laptop, and honestly, I'm expecting this to fail spectacularly. Wait, it's working. Bootloader is loading. Open Inverter program is flashing. Everything worked on the first try. That was way too easy. I think I will pay for that later. Now, here's the fun part. JLC PCB parts inventory is about as complete as my planning skills. So I get to hand solder all the missing components. Joy. Moving on to carefully assembling and soldering the remaining bits, because apparently I enjoy tedious tasks. Time to program the ESP32 module. For this, I need a SparkFun FTDI board. It's basically a fancy USB to UART converter. Also, I have to pull the I/O pin low by connecting it to the ground. This puts the ESP module into programming mode, which is a fancy way of saying, please accept my code. Well, I loaded up Microsoft Visual Studio Code with Platform I/O and loaded the code for the ESP32. Entered the programming mode. Let's do this. Success. Programming complete. Now let's check Wi-Fi. Looking for the module in the list. There it is. Connecting. Oh, well connected. Launching the web interface and we are up and running. Yes, that's working as well. If you watch one of my previous videos, and if you didn't, I don't blame you, but if you were, you would have known that I successfully bench tested the new design PCB. But before I connected it to the actual Tesla motor, I decided to test the original Open Inverter board to make sure that my setup with the power supply and contactors working correctly. And of course the contactors just gave up on life. Now I'm going to reveal what went catastrophically wrong. Spoiler alert, it was a user error. Shocking, I know. I'm an idiot. I was hitting the current limit. See, right now there are 2 amps. And if I turn it on, the current limit light is on. No contactor clicking. I bumped it up a bit, but it didn't help. Then one of my brilliant viewers commented that he had the same issue, the current limit. And I smugly replied, I already checked that, that is not it. But later I thought, wait, what if I really increase the current limit further? Let's try 4 amps. Turn it on and contactors are working. They are alive. With the increased current limit, contactors started to work. But I immediately ran into another issue. The pre-charge contactor would close only to open shortly after timing out. It didn't take long to figure out why. The Open Inverter software has a parameter in the contactor control section called UDCSW. This parameter is there to ensure that the main contactor can only be closed after the voltage on the inverter reaches specified value. I set this value to 100 volts. However, despite the fact that my high voltage power supply was delivering 120 volts, the system wasn't working as expected. And when I checked UDC voltage reading in the software, it was reading unexpectedly low value, just 2 volts. I could see that 120 volts was reaching the pre-charge contactor, but I needed to check the voltage at the main contactor, straight after the pre-charge resistor. When I did the check, the voltage was super low. That made me think the issue might be with the pre-charge resistor. I took it out and measured its resistance, including the wires. It was very high, about 1 megohm. That's way off, since the resistor should only be about 25 ohms. I thought one of the wires might be damaged. So I stripped out the insulation and measured directly on the resistor legs. But the high resistance was still there. This caught me off guard. I'd never seen a resistor fail like this before. To be sure, I checked another resistor I had lying around, thinking maybe my multimeter was acting up. But no, the other resistor measured perfectly fine. So I did find a culprit. The pre-charge resistor was definitely faulty. As I did not have suitable replacement resistor, I had to improvise. I used 4 3.3 ohm resistors connected in series. To be sure, I had to check the total resistance of my improvised pre-charge resistor, and it was about 17 ohms, about the value I expected. In the end, I had to just isolate my newly made pre-charge resistor, and it was ready to be tested with the motor. I have relocated to the motor and installed the pre-charge resistor. Since there is plenty of space in the contactor box, I am now ready to run a test. Okay, power is on now. Yes, it's working. The contactor only closed once and it's staying closed. Okay, so I'm now measuring the voltage on one side of the contactor and it's 120 volts, and then on the opposite side of the pre-charge resistor and it's also 120 volts. That means it's all working. I'm going to press start button. When I press start button, I'm hoping that this will open and this will close. We might as well try to switch direction. Okay, direction switched, and we need to apply the throttle pedal. Alright, I finally got the motor spinning again with the original Open Inverter board. It feels so good to have it back up and running. Honestly, this was the plan from the start, but I made things harder for myself. Instead of building a new wiring harness and contactor setup for the zombie inverter, I reused my old Tesla contactor box and some of the wiring as well. When I tried to switch it back, it didn't work right out of the box. Lesson learned again. I really need to start documenting my setups and stop messing with them mid-project. But hey, that's all part of the process, right? Now I can move forward and install my Tesla board prototype into the inverter. Let's see if I can get the motor spinning with that setup too. First things first, I need to free up the motor from all of the attachments so I can gain access to the inverter. Remove the contactor box, disconnect the inverter and remove high voltage cables. Alright, now the motor is free, it's time to get this inverter out of the way. First I have to tackle the 3-phase cables that are hiding behind this lovely orange cup. Once those bolts are undone, I can go ahead and remove the cover bolts as well. Almost there. But hold on, not quite done yet. There are still 2 internal connectors holding things together. One for encoder and one for the temperature sensor. When those are out of the way, I can finally detach the inverter from the motor and call it job done. Inverter's out. With the inverter on the bench, the next step is simple. Remove the old board, solder the current sensors onto the new one, and we're good to go. When I first removed the Tesla PCB, I had to take out the entire base plate off, carefully sliding the fitting through the high voltage cables. But now it's much easier. Since my current sensors aren't potted into the base plate anymore, I can just remove the Open Inverter board directly. Let's get started. Just a few screws to undo and release the plastic clamps for the connector, and the board is out. Before moving forward, I needed to check if the new PCB would fit onto the inverter's top plate. I was happy to see that the holes lined up very well. For soldering the sensors, I started by measuring the height of each sensor on the original Open Inverter board. To position them accurately, I secured each sensor from the bottom by soldering 2 of the 4 side legs. Once that was done, I finished soldering them properly from the top. With the sensors in place, the board was ready to be mounted onto the inverter. I reinstalled all the screws, reattached the PCB to the inverter, and now it's time to fit everything back and get ready for testing. Let's see how it performs. But when I started testing my new board, it did not work. Well, I'm not gonna give up that easily. I'm gonna have to investigate. I opened up an inverter again, and this kind of became a routine for me. I can do it much quicker now than I did it first time. But this time I need to position the inverter very close to the motor part, so I can connect the shorter cables for all of the 3 phases of the motor. Well, at this point I want to solder on some of these tiny wires that will allow me to test the board safely. So first I want to solder accelerator, and this will be one of the PWM signal connections. What is PWM, you may ask? Well, this is just a square wave with a fixed frequency, but it can have a changeable width. This signal is called pulse width modulated signal. In electronics, this signal is often used to control speeds, things like the speed of the motor or LED. Once the board was installed, I connected my oscilloscope probes, one to the throttle signal and another one to PWM signal. With the system powered on and probes connected, I can start measuring my signals. First I will do the throttle pedal. So the blue signal on the scope shows the throttle signal change, and when I press the throttle pedal, it does increase. So the throttle signal is indeed getting registered. Next I check PWM signal, and as soon as I press forward switch, I was getting the 1, but it wasn't changing in response to my throttle pedal. I had to analyze what did I do wrong. I found a few mistakes in my design. First, I had mistakenly swapped the connections for the current sensor 1 and 2, but after swapping them back over and running the test, PWM signal still wasn't changing. While reviewing the schematic, I observed that MC74HCT chip was driving the PWM. I realized I had mistakenly used MC74HC chip instead. I've replaced the HC chip with the correct HCT version, but it still did not work. Oh dear. At this point I decided to reflash the Open Inverter program onto the STM32 chip. And now what I'm going to do, I'm going to press start. Now the main contactor is on. And hooray, it worked. Seeing the motor finally respond as expected was an incredible relief. The combination of the Open Inverter board, my custom layout and ESP32 integration was working as planned. Alright, we're getting there. I'm so pleased and so relieved it's working. If you want to follow up on my future videos, make sure you subscribe, make sure you like, share, and I will see you on the next one.